All right, we are doing chapter 11, and the first section in chapter 11 concerns what we call prime factorization. One of the major results with prime numbers is that you can write any integer as a product of prime numbers, sort of emphasizing the fact that the prime numbers are very much the building blocks of all the integers. So we're going to do that by way of what we call a factor tree. And the easiest way to explain that is to just look at an example. So example or exercise 11.1, use a factor tree to determine the prime factorization of the following numbers. First up is 100. So exercise 11.1, number 1. So we're going to write the 100 up here, and then all we do is split it into two factors at a time. Whatever two factors you see first, for example, I see a 2 and a 50. 2 times 50 is 100. So I'm going to split it like that. Then I go as far as I can until I hit the prime number. 2 is already a prime number, so I'm not going to do anything with that. 50 is not. 50 can be split up into, for example, 5 times 10. 5 is a prime number, so I stop. Even sometimes some people like to circle it to indicate I stopped there. 10 is not a prime number. It can be split up into 2 and 5. Circle, they're both now prime numbers. All the paths have been followed until the end, and I'm done. Just to show you here that, so now we can write 100 as 2 times 5 times 2 times 5. Notice that I wasn't restricted to splitting it in any particular way. I could have seen, well, I like 4 and 25 as my first split. It's perfectly fine. 4 can be split up as 2 times 2. 25 can be split up as 5 times 5. And so from this tree, it would be 100 is 2 times 2 times 5 times 5. But regardless, in both cases, 100 is made up out of 2 2s and 2 5s. And we can write it perhaps in a more condensed way by using powers of 2. There are 2 2s multiplied together, and there are 2 5s multiplied together. Even though all of these are the same, we're going to use this more condensed version of the factorization of the number so I can see how many prime numbers are used and how many times. So there's the prime factorization of 100. Now we'll just do a couple of these to make sure. The next one is 294. Let's see if I have enough space here for 294. I should. Number 2 is 294. Whatever split you see first. You don't have to be creative. You don't have to think of fancy numbers. The one I see first is a 2. It's an even number, so I know it's divisible by 2. So I'm going to use a 2. Now, 294 divided by 2 is going to be 100. Now, you can use your calculator, or you can do long division. You can do whatever you want. 147. Now, it might seem like, ooh, 147. Well, 2 is prime for sure. Is 147. Should I stop? Well, based on the previous chapter, we know some divisibility rules and a way to also test if this is a prime number. What can I do? Well, it's not even, but the sum of the digits, 1, 5, is 12, so I know this guy is divisible by 3, maybe by some other numbers as well, but 3 is the first one I see. So then if I divide this 147 by 3 to get the other factor, that's going to be 49. 3 is a prime number, so my path stops there. And 49 is obviously 7 times 7. So using the circles makes it easy to see what all my numbers are. Kids often don't do that and then miss early numbers. And so by the circles, I have a 2, a 3, and 2 sevens. Sorry, that almost looks like a 3, 2. We don't write a 2 to the 1, 3 to the 1, though you can. It's totally optional. Or if there's nothing there, it's obviously just one of them. So that's the prime factorization of 294. We'll keep going. Next one is 702. 702. Let's go to a new page here. That'll be number 3. 702. Now you could think, well, I could just use a 2 if I want to. I can get fancier. Really doesn't matter. Let's go with a 2. Since I don't have a calculator, there's no point in wasting time looking for bigger numbers. The tree might look different than someone else's, but the prime factorization is always going to be the same. So that is going to be 351. Now 2 is done. 351, is that prime? No, I can add up the digits as a check. That adds up to 9, so I know this guy is divisible by 3 or 9. You can use a 3, you can use a 9. Now, just to mix it up, let's use a 9. So 9 goes into 351. How many times? Well, it goes into 35 3 times. 8 is left, so 939. 9 splits into 3 times 3. 39 can split into 3 times 13. And they are all prime numbers. Usually we have examples that end in small prime numbers, but there could be one that's a little larger, and you do have to make sure that you should stop. Excuse me. So my prime factorization of 702 is 2 times 3 to the 3 times 13. Let's do one more. The number 240. So set up the tree diagram. With 240. That's number 4, 240. And take a minute to think, what is your first split that you want to do? This one has many options. I can maybe get a little creative and do 10 and 24. 10 splits into 2 and 5. 24 splits into whatever, 4 and 6 maybe. The 2 is a prime number, so I stop there. 5, but not 4. That's a 2 and a 2. And not 6. That's a 2 and a 3. Now I'm done with each path, and my prime factorization of 240 is, how many 2's do I have there? 4, just one 3, and just one 5. 240 by way of a factor tree. So that is the only thing that we're looking to do in section 11.1. 11.1. What is this line doing here? Whoopsie, I want to erase. Sorry, I'm getting a little sidetracked here. That line is messy. So the first step is to be able to factor a number. Next up, we have, zoom in, 11.2, which is the greatest common factor or divisor. Sometimes people use factor, sometimes people use divisor. Doesn't matter really. Now we're going to introduce this concept by way of an example. Example 11.1. You have 24 pieces of Halloween candy and 30 pieces of regular candy, and you want to divide them equally among some children. What is the largest number of children you can accommodate if both types of candy are to be divided equally? So one thing we can do is look at 24 and 30. So we have 24 and we have 30. And we can ask, well, how many, if we just look at them each separately, how many children can we accommodate with 24 if everyone should get exactly the same amount? We can have one child, we can have two, we can have three, we can have four. How many pieces of candy does each child get if we have 4 kids? Well, that is the concept of division. 24 divided by 4, each one will get 6. I can't have a 5. No. Let's go backward there. Not 5. But I can have a 6, and then every kid will get 4. So really, the list that I'm making here is a list of factors or divisors of 24. Not 7, 8 can divide into 24, 9, 10, 11, 12, and then the next one will be 24. I can do the same thing for 30. All its divisors, all its factors, 1, 2, 3, not 4, 5, yes, 6, 7, 8, 9, 10. Then I'll go up to 15. And of course, the number itself. I could accommodate, if I'm just looking at the 30, I could accommodate 30 children. And each one will just get 1. So now the question is asking, where am I now? What is the largest number of children I can accommodate if both types of candy are to be divided equally? So the largest number common to both of these lists is 6. And we say the greatest common. Now I'm just going to use factor to be consistent with our book. And I think most people say factor, but divisor is also acceptable. The greatest common factor of, you have to say which numbers you are looking at. 24 and 30, greatest common factor is 6. Now that's a lot of words to write. It's not that I'm lazy, but I want to be efficient. So mathematically, we write GCF, or some people write GCD, and in brackets the numbers in question, 24 and 30, and then the answer. Now, in lower grades, you would certainly do it like this, and they would make lists of factors of a number and then pick from that list. But a natural response to this method could be, if these numbers are big, my lists are going to be huge. and it's extremely tedious to do it this way. If we understand how integers are built, what are their building blocks, what makes them tick, we can maybe sidestep this unnecessary work. And prime factors give us a way to do exactly that. But first, let's look at this 24 and 30. Now, I don't think we've done them yet. We've done 100, we've done 294, we've done 702 and 240, and these numbers will come up again in examples just for convenience. Let's do 24's prime factorization by way of its factor tree, though it's not necessary to do a tree. The number's fairly small. You can do a 4 and a 6, and that splits up into a 2 and a 2. They're both done. And 6 splits up into a 2 and a 3. So 24 is 2 cubed times 3. 30 splits up maybe a 2 and a 15. And 15 can be split 3 and 5. And then I would be done. So 30 is 2 times 3 times 5. Now pretend you didn't know what the greatest common factor of 24 and 30 is. How do I use these building blocks of these numbers to find and essentially build this GCF? Well, 24 is built up from 3 2's and a 3. What is the greatest common factor, greatest common divisor? It's a number that has to divide into 24. So whatever my answer is, whatever pieces I use in my answer, they can only come from these pieces in 24 because they have to fit into 24. They have to divide into 24. But the same goes for 30. Whatever pieces I use in my answer for this greatest factor has to be a factor, meaning it has to come from a 2, a 3, and a 5. So because a 2 is common, I can use a 2. I can't use too many. Yes, 24 is going to be happy if I use 3 2's because they'll all fit in. But 30 says, no, I only have 1 2. You can't use more. You won't fit in then. So I'm restricted to only a single 2. I can also use a 3 because it's common to both, but only 1 because both of them say, nope, only 1 can fit in. So now this number, excuse me, this number, 2 times 3, can fit in there and can fit in there. Not at the same time, but the requirement is this number has to fit in there, this number has to fit in there. And it's the biggest one I can make. I can't use a 5 because though 5 will be able to fit into 30, there's no 5 in the makeup of 24. So if I use a 5 here, this answer is not a factor. It doesn't divide into 24 anymore. So that is the reasoning that we're going to use. Now, let's look at an example. There we go. I'm going to scroll like this. Exercise 11.12. I think I'm on this page. Let me go here. 11.12. 2, sorry, not 12. First one. I'm looking to find the greatest common factor of, can't remember, 90 and 360. Whoopsie, where am I now? There, 90 and 360. I want to know, what is that? Well, instead of making a list of all the possible factors, that would be ridiculous. I am going to look at what makes these numbers tick. So I'm going to have to find the prime factorization, and I'll do that by way of a factor tree. So I can go 9 times 10. That's an obvious one. 9 is 3 times 3. 10 is 2 times 5, and I'm done. So 90 is 2 times 3 squared times 5. And then we'll also do 360. What's an easy split? Maybe a 36 and a 10. That whatever comes to mind first, honestly. 36 is 6 and 6. 10 is 2 and 5. The 2's done, the 5's done. 6 is 2 and 3. Done and done. The 6 is 2 and 3. Done and done. All right, 360. How many 2's do I have here? 1, 2, 3 2's. How many 3's? 2 3's. And a 5. All right, so there are the prime factorizations of these numbers. Now, how do I build this greatest common factor? Can I use a 2 in its building? Yes, because a 2 is common to both. How many 2's can I use so that this answer, the GCF answer, still fits into either one of these? I can only use a 1 because this guy just has 1. I can use a 3 because it's common to both. How many 3's can I have in here? Only 2, because 90 only has 2 3's, and 360 also only has 2. So both of them would be happy with 2. I can also use a 5 because 5 is common to both. How many 5's? Just 1, otherwise it won't fit into these guys anymore. Now, I'm not that interested in what that answer is, more in how we got the answer. So feel free to calculate that or not. Really, I don't care. I want to see this detail. That is what I'm interested in. The how is much more important than the what is the number. How did I get it is much more important. So if we look at number 2, we have to find the greatest common factor of 100 and 240. But let's write it down here. This is number 2, greatest common factor of 100 and 240. But hold on a second. I already did the work. 100 was here. 2 squared, 5 squared. 100 is 2 squared, 5 squared. And 240, did we do 240? I thought we did. There it is. 2 to the 4, 3, and 5. 240. 2 to the 4, 3, and 5. All right, so how do I build this number? Can I use a 2? Yes, 2 is common to both. So what we are noticing now is we are using prime numbers, or prime numbers, yeah, common to both factorizations. Then, how do I choose the power of 2? In other words, how many 2's can I have in here? I'll choose 2. Because any more, and this answer, this GCF won't fit in here anymore. So I'd have to choose the lower of the exponents. The lower exponent. If I use a 4 there, yeah, I can fit into 240, but not 100. And it has to be a common factor. So can I use a 3? No, there's no 3 in 100. I can use a 5. How many? Only one. Only one, because there's only one. And there's my answer. One more. 702 and 94. GCF of 702 and what? 294. 294. I believe I've done these. 294 is 237 squared. 294, 237 squared. 702, 702, 702. 2, 3 cubed, 13. 702 is 2, 3 cubed, 13. I'll just double check that. Yes, all right. So now, how do I build the GCF? Common prime factors, 2, 3, and that's it. For the 2, the lowest exponent is 1. For the 3, the lowest exponent is 1. And you're done. It's really that simple. But before I got to this recipe, I needed to understand how numbers are built. What do I mean by the GCF? And how can I use the building blocks of each number in combination to build this GCF? And the concepts and the how is more important than just following a little formula and a recipe to find the answer. All right, last section, very similar to this one, 11.3 is called the least common multiple. And we're going to do that by way of an example as well. Hot dogs are sold in packages of 10, while hot dog buns are sold in packages of 8. Now I'm hungry. Anyway, how many should you buy of each so that the number of hot dogs is the same as the number of hot dog buns? A very interesting marketing strategy is to do something very similar, that the number of hot dogs and the number of hot dog buns in the package are not the same. So you're always left with a little bit, then you buy some more of the others, then that's left over, then you buy, and back and forth, and you end up spending much more than you needed to. So, excuse me, hot dogs sold in packages of 10. Hot dog buns in packages of 8. So how many hot dogs will I have, assuming I don't eat any? I'll have 10. Sorry, hot dogs or hot dog buns? I'm a little confused. Hot dogs are 10. I can have 20 hot dogs, 30, 40, 50, 60, and so on. It never stops. And I'm looking for multiples of 10. Hot dog buns, though, I'll only have 8, 16, 24, which are the multiples of 8, 32, 40, 48, 56, and so on and so on. Never stops. Now what's the question? Question is, how many should you buy of each so that the number matches? Same number, common to both lists. It is right there, 40. So I'm looking for the lowest number. The lowest number. There are other numbers, right? If I keep extending my lists here, let's make some space. I'll have 70, 80, 90, and this one would be 64, 72, 80, 88. So there will be another one that matches, but it's not the lowest. It's not the lowest. 40 is the lowest. So we say the For some reason, we don't say lowest, we say least, which I find quite annoying, but everyone says that, so I guess I have to conform and say it too. We say the least common multiple of 10 and 8 is 40. Now that's a lot of words. We write this in a more compact way, LCM, the numbers in question, and the answer. So this one stands in contrast to the greatest common factor. If you recall, oops, over here I think, greatest common factor was a number that divides into both of these. Now this is not the case with the least common multiple. Both of these numbers divide into the answer. So it's sort of backwards, I guess. Sort of the opposite concept, if you will. So, but the question is now the same. If these numbers are a little different, then these lists can get really long before I find the lowest, the least common multiple. So maybe I can exploit how the numbers are built by way of their prime factorizations to construct this smallest multiple of both. So let's see. Well, 8 and 10 are pretty easy numbers to work with. 8 is 2 cubed. 10 is 2 times 5. How can I build this 40? Well, now remember, both of these guys have to fit into 40. So I'm going to have a 2. And I'm going to have 3 of them, otherwise 8 can't fit in. And if I leave it like this, 10 can't fit in unless there's another 5. Now 10 can fit in, and 8 can fit in. Not at the same time, but that's not the requirement. They just have to be able to divide into this, be factors of this number. This number has to be a multiple of that, meaning it has to contain its prime numbers, its prime factorization, and some other stuff maybe as well. So, by way of example, we'll see if we can establish some rules to figure this out. Let's go to our first example. Exercise 11.3. Let's do it over here, 11.3. And we're looking in the first one for the LCM of 90 and 360. 90 and 360. Now, a lot of the work has been done for us because I already did the factors of these. Where are they? 90 and 360. 90 was 2, 3 squared, and 5. 2, 3 squared, 5. 360, oopsie, was 2 cubed, 3 squared, 5. 2 cubed, 3 squared, 5. If I didn't have this, then I would have to do these factor trees again, but we've done it once, there's no need for that. All right. How can I now construct this answer, which has to be a multiple of both of these numbers, but the smallest possible I can make? Now, because it has to be a multiple of both, I'm going to have to use a 2, have to use a 3, have to use a 5. If I don't have these prime numbers, these guys won't be able to fit into this answer, and they have to. Now for 90 to fit in, I'm going to have to have 2 3s. Now 90 says, yeah, I'm happy. I can fit in. I'm good. 360 says, ew, no, it's close. I'm not there yet. I need 3 2s. Now I'm happy as well. Again, you can calculate that, but I like to see the detail. I'm more interested in how we got there than what the actual final number is. Okay, let's do some more examples and see if we notice anything. 100 and 240. LCM of 100 and 240. So that 2 does not look great. Now again, I will use the fact that we already know these guys. 100 is 2 squared, 5 squared. 2 squared, 5 squared. And 240 is 2 to the 4, 3, 5. 2 to the 4, 3, 5. All right. Now, 100 says I'm going to need a 2 and a 5. 240 says, oh, I need a 3 as well. Hold on. 3, 5. 100 says, I don't care about your 3, but I need to see 2 2s, 2 5s. Now I'm good. It's the minimum I need to see. 240 says, I have my 3. I just needed 1 5, so I'm good. But I don't have enough 4s. I have too many 4s, and I can't fit in. So please update this to 4 4s, 4 2s, and I'm happy as well. And there you go. So now, how do we find this? Well, I need to use all the prime numbers that I see in my list. Not all prime numbers that exist, of course, all prime numbers in question. We've always done that here as well. 2, 3, and 5. 2, 3, and 5. Every prime number I see has to go in. Then when it comes to the exponents, which ones do I use? I now use the largest one that I see. So I choose the largest exponent for each. In the case of the 2's, 4 was the largest exponent. In the case of the 3's, it's only this guy, 1. In the case of the 5's, 2 was the largest exponent. And there you go. Let me just add a page. I miscalculated the number of pages. 1 second here. And we have one more example, number 3. And that is 207, 294. So LCM, no, not 207, 702. 702, 294. 702, you sound familiar. 702, 2, 3 cubed, 13. 2, 3 cubed, 13. 294. 2, 3, 7 squared. 2, 3, 7 squared. Let me just double check here. It looks good. Okay. Now, what have we seen? I have to use all the prime numbers that I see here in these two factorizations? Largest power of 2, a 1. Largest power of 3, a 3. Largest power of 7, a 2. Largest power of 13, a 1. And I am done. So don't look too much at this and stop thinking. Any sort of formula, any sort of generalization, any sort of shortcut automatically encourages us to stop thinking. I want to know, why is this the way it is? How do I find it? Not just, can I do it? But why are we doing it the way we are? All right, thank you.